Good morning, we are Group 9. Our topic is Solution Process 1, which the title of journal is Efficient Tandem Solar Cells with Solution Process Perovskite on Textured Crystalline Silicon. In this presentation, first I will give a brief introduction and background. My teammates will then describe the strategies and mechanisms. The power conversion efficiency for single-junction solar cells is limited by Schottky-Kreiser limit. An effective approach to realize high efficiency is to develop multi-junction cells. Inorganic perovskite solar cells (PSC) have attached great interest over the past 10 years. Perovskite solar cells' power conversion efficiencies have risen from an initial 3.8% to 25.2%. A combination of material features such as the minimal energy needed for crystallization, the sharp optical absorption edge, and the adjustable band gap perfectly suit for a solar application, which has led to advancements. By using solution-based coating technique to deposit the semiconductors, it further facilitates the development of PSC. The efficiency level can be increased to more than 33.7 theoretical limit by reducing the thermalization losses through the stacking of absorbers of decreasing band gaps. Moreover, the anti-reflection foil's efficiency may be diminished after encapsulation. Thus, recently focus has been shifted to using completely textured silicon with combination of perovskite.
My part is the strategies. Silicon heterojunction solar cells, which is also called SHJ, are electronic devices formed by depositing an amorphous silicon film on a crystalline silicon absorber layer. They have excellent properties such as high efficiency and simple tandem integration, so silicon heterojunction technology is used for tandem solar cells in the paper. This figure shows the structure of the silicon heterojunction technology, and we can see it includes two semiconductors, crystalline silicon and amorphous silicon. Surface passivation technology has also been applied in the paper. Surface passivation can improve the electrical properties, photoelectrochemical stability, and photoluminescence intensity on the surface of the material. In the paper, a surface passivation strategy is introduced by occurring a self-limiting passivant on the perovskite surface. This strategy increases the carrier diffusion length and surprising phase segregation. Here's a schematic of a PRC-type silicon solar cell with the surface passivation. Front-side texturing technology can be mainly applied to improve the efficiency of solar cells. By introducing surface textures on the silicon substrate, the reflectivity on the surface can be reduced, and more absorbed light energy in the solar cell can be converted and the efficiency is improved. Texturing is to etch a single crystal silicon wafer with a certain orientation in alkaline solution, and a pyramid-shaped structure will appear on the surface of the silicon wafer. These pyramid structures can increase the ability of the single crystal silicon wafer to absorb incident light and reduce the reflectivity to improve efficiency, and as well as reducing losses. When perovskite was deposited using solution techniques on pyramid textures on the silicon surface, it was found to be inefficient and at collecting charge and had a shortened path. A more efficient microsilic perovskite cover pyramid was developed using solution processed perovskite with micron band gap, which is combined with pyramid textured C silica instead of solution processing directly on C silica, which improves the efficiency of charge collection in the solar cell and also enables higher depletion.
Okay, so come to my part of the strategy. The author first introduced the strategy of concentrated precursor. When the perovskite film was deposited under conventional planar perovskite fabrication conditions, the pyramids that were not capped with perovskite were absorbed, and these regions created shunt paths in devices. So the authors naturally used the concentrated precursor to completely cover the pyramids. This results in a micrometer thick pyramid perovskite with large grain size. It was able to achieve uniform perovskite coverage of the pyramids using this method, as we can see in the figure on the right hand side. This eliminates the need for additional flattering process. In addition, in order to achieve current matching, instead of reducing the thickness of a smaller bandgap perovskite, the authors broadened the bandgap of the micrometer thick perovskite, and this perovskite with a very wide bandgap, which is usually around 1.68 electron volt, paves the way for tandem solar cell to achieve higher ultimate efficiency limit. And since thick perovskite layers necessitate long charge carrier diffusion lenses for efficient charge collection, and this condition necessitates the use of perovskite crystals and surface with high electronic quality. So several surface treatments were focused to improve the performance of single junction wide bandgap PSS. And TOPO is one of them, which is an organophosphorus compound with the molecular structure on the right-hand side figure, used to significantly reduce non-radiative recombination while increasing perovskite stability, but its insulting property makes it inhibit the charge transfer in the device. And the author also used another method, which is exposing the rough top of the surface of perovskite to 1-butanethol vapor, and found that prolonged exposure did not harm the perovskite. This is based on the self-limiting passivation, which is also called SLP of the Thorio group. No attaching sites for additional layer growth after the initial passivation, which ensures the damage of perovskite will not happen, and the detailed mechanism of SLP of the group will be talked about later in the mechanism part.
In this part, I'm going to introduce the mechanism of self-limiting passivation. Since early solution and physical vapor deposition techniques face challenges to fully cover the silicon pyramids, as due to the relatively high roughness of the perovskite film, the charge collection does not meet the expectations. So, the researchers applied seal self-limiting passivation treatment on the perovskite film to enhance its properties. Seal passivation has many advantages due to the presence of the alkali group within the structure. The hydrophobicity is well enhanced. Therefore, the SLP treatment could improve the phase stability and device efficiency of the perovskite under different conditions. Moreover, as the perovskite layer is relatively thick as shown on the right, the charge carrier diffusion length must be further enhanced. An ideal solar cell should have an almost equal rate of charge recombination and charge generation. However, for perovskite, it's hard to achieve due to the potential defects within the structure. Unlike the well-controlled manufacturing crystalline silicon semiconductors, the crystal growth of perovskite is much faster and rough. Consequently, it will generate polycrystalline films, which may lead to the formation of structural defects. These defects may act as recombination centers, which affect the PV parameters and the device stability negatively. Using the SLP, the region with relatively high defect density, like the grain boundaries and outer surface of the perovskite, could be minimized. In this case, seal molecules, due to their self-limiting nature, no entering site will be present after initial passivation, which prevents the potential further damage of the perovskite.
I'm going to be talking about the depletion region modification in textured silicon tandem solar cells with spin-coated perovskite, which help increase the charge carrier collection. Before I move ahead, allow me to introduce a characterization method known as Kelvin probe force microscopy. It helps to map the work function of a sample at a nanometer scale. A DC bias is applied at the probe tip to cancel out the electrostatic force, from which the Fermi energy level can then be calculated. In this work, the authors measured potentials across three cross-sections. for the textured tandem cells at the silicon pyramid peak and valley, and also for a flat silicon tandem solar cell. This gave the following potential profiles as shown in figures D, E, and F. By taking its derivative, the electric field distribution are extracted in figures G, H, and I. From this, we can see that the distribution is similar at the perovskite ETL interface, as it is identical for all the three. But there is a significant difference at the perovskite HTL interface. The electric field extends far deeper near the pyramid valleys for the textured tandem cell. This electric field is due to the depletion region where the carrier motion is drift dominant. So the depletion region is the widest where the perovskite is the thickest. This is beneficial for the charge carrier collection as diffusion alone may not be sufficient to move charge carriers in a micrometer thick perovskite layer. Such geometry controlled depletion width is not seen in a flat silicon cell and also in alternative deposition methods such as thermal co-evaporation. This is a testament of the superiority of spin-coated perovskite in a textured silicon tandem solar cell. Finally, the phenomena discussed in the presentation were verified through the solar cell parameters. Figure A shows the tandem solar cell device architecture, and in Figure B, the JV curves are compared. It is seen that the solar cell in this work has the highest open circuit voltage and short circuit current and fill factor. The maximum power conversion efficiency was observed to be 25.7%. The device also showed remarkable stability of 400 hours under 85 degrees Celsius and 45 to 50% relative humidity. On the behalf of Group 9, thank you for listening.